Yeah, thanks again for your great lecture.
Oh, yeah, yeah. Oh, of course. Yeah, glad to look at it.
All right, it's 5:30, so let's go ahead and get started. Good evening, everyone. How's everyone doing today? Good, good. Thumbs up, thumbs up. We're in week 12, so you know it's we're in the end game now, and so it's you know we're definitely getting close to the end of the semester. So you know everyone hang in there. I know this is time when everyone gets tired, so you know we're almost at the end. Okay. All right, and so today I have just a you know a one lecture kind of topic that I want to go over. It's about verification and validation. Okay, and so you know I think this is one of the more important things to discuss in terms of finite elements. It's a little bit it's quite different than I think everything we've discussed so far, but I think it's something important, and I think it's something that doesn't really get discussed enough in the classroom. And so you know I want to make sure that you guys leave this class you know with an understanding of what this is and why it's important for finite elements. Okay. All right. And so let's see. So we have one after this class, we have one more week of instruction, and then we're on Thanksgiving break. And so on Thanksgiving, you know, there's no classes over Thanksgiving, and so you know we have the entire week off there. Okay. And then when we come back from Thanksgiving, we'll have just 2 weeks of instruction. Okay. And so in terms of, you know, what's left for the class in terms of, you know, what we're going to do, I do have 2 more activities planned. And so we have an activity next week, and that's going to be based on modal analysis and basically frequency response. Okay. And so if you're interested in vibration or structural vibrations, then, you know, that's going to be an interesting activity for you. And then my last activity after Thanksgiving is going to be about buckling. Okay, and so a Buckley analysis is another type of analysis you can do in ANSYS, and we'll talk about how to do that after the break. Okay. All right, and so I think that's all the announcements. And so, are there any questions I can answer before we get started? Okay. All right, so let's go ahead and get rolling. All right, so the topic for today is verification and validation. So, you know, let me start this topic off by saying that, you know, we've been at this for 12 weeks now, so we've been at it for almost 3 months. And, you know, we've gone from all the way at the beginning where, you know, just introducing what finite elements is to now where I think you guys, I'm confident that everyone in this class can run a complex and complete finite element simulation. Okay, so we've come a long way just to get to where we are right now. Okay, and so, you know, at this point in the semester, you know, we've basically seen, you know, that finite element simulations can be extremely powerful tools for engineering analysis and design. Okay. Okay. And so what is it useful for, right? And so the main thing that it lets us do is that it lets us simulate physical situations or real life situations without having to do any kind of physical test. Okay. Okay. Right. And then once we've run those simulations, you know, we can view the results, and the results that we get are very detailed, right? And so we get very detailed descriptions of what the deformation field looks like, and you know what the stress distribution looks like, and all of those things. Okay. But you always have to remember that, you know, even though finite elements, you know, it's a great tool, at the end of the day, it's just a tool. Okay. And in particular, you know, when we're solving finite element problems, you have to remember that they're only an approximate solution. In other words, what we could say is that finite elements is only an approximation of reality. Okay. Another way that we can say this is that when we run a finite element simulation, it's simply just a model for reality. Okay. Okay. And so a model is a very general term. Okay. And so model is nothing more than just something that represents something else. Okay. And so within the scientific and engineering realm, what we say is anything that's a model is just something that represents a physical phenomenon. Okay. A model is something that we can use to substitute, a real life test, real life situation. Okay. And so there's tons of different models out there. Okay. And so, probably the ones you're probably most familiar with are known as mathematical models. Okay. And so when someone says that, we have a mathematical model for something, all that means is that they're using equations and they're using numbers and data in order to approximate reality or to give us a sense of reality. Okay. And of course, finite elements fits within this category of mathematical models. Remember, finite elements ultimately, at the end of the day, we're solving differential equations, and those differential equations are used to represent, what's supposed to happen in real life. Okay. All right. Any questions on this so far? Right. So ideally, even though we say finite elements is just an approximation, in order for it to really be useful, we want it to be a good approximation, right? And so we want it to be as close to reality as possible. Okay. So let me give you an example here that kind of shows you, the range of different models that are available. Okay. All right. And so let's say that we have my favorite example ever. And so let's say that we have a cantilever beam. Just because it's so easy to draw. Okay. Right. And so let's say that we're applying a force at the end of this beam. Okay. All right. So let's say the force has a magnitude P. Okay. And so from this beam, let's say that let's say that we have an objective in this analysis to find out what the maximum stress is in this beam. Okay. All right. And so, in order to answer this question, there's a few ways that we can go about it. Okay. And so first of all, we can actually run the physical test. And so we can build this beam to the exact specifications. We can apply the load, and then we can use some kind of force meter or something to measure the stresses. Okay. But that would be pretty troublesome, and that would take a lot of work. Okay. And so a better way to do this is, let's use a model to predict what the stress is. Okay. Okay. And so one model that you can use is finite element simulations, right? Okay. And so if we wanted to simulate this in FEA, we would get a CAD model for this beam. We'd load it up into ANSYS, we mesh it, we'd apply the boundary conditions, and then we'd run the simulation and find it out. Okay. Okay. And so that's one way that we can approach this. That's one way we can answer that question. Okay. Another way that we can approach this problem is we can use analytical methods, right? And so let's say that we use a beam equation. And so let's say that we use a Euler-Bernoulli beam equation. Okay. Okay. And so that's another model that we can use. Okay. And so, ideally that we would hope that, both option 1, option 2, they're going to give us the same solution, or they're going to give us something very similar. But there are basically 2 different models. Okay. And a third example, you can just, the definition of a model is so broad, right? And so it's something that just we're using to predict reality. Okay. And so another example that you can do is you can just ask your cousin. Okay. And, we can assume that your cousin is maybe, 7 or 8 years old, doesn't really know what's up with the world, but, you can ask them, you can give them the situation and say, hey, Jordan, what's the stress in this beam? Can you tell me? And so, and your cousin, being enthusiastic and, thinks he's smarter than everyone else, he'll give you an answer. So maybe he'll say that the stress in this beam is 5. Okay. And I actually did ask him this, and this is the answer that he gave me. So, and so you ask him, 5 what? What is 5? And he said, he just says 5. That's it. Okay. And so, obviously this is not helpful, right? But technically it's a model, right? And so, you ask your little baby cousin and they give you an answer, and technically this is a model, right? And so, because it's you have a physical situation, you don't want to actually test it, and so you make a prediction based on something else. Okay. And so with that said, obviously asking your baby cousin is not a very good model, right? And so, we have kind of a range of different options here. Okay. And so, the whole idea with verification and validation is to say, or is to assess, how good is one model compared to the other one. Okay. Okay. All right. There's a very famous saying too, before we kind of move on from models, that, there's a famous saying from a researcher that said all models are wrong, but some are useful. Okay. And so that's very true. And so, no matter what kind of model you have, no matter how sophisticated it is, I won't say it's impossible, but it's very, very hard to get to match reality exactly, right? And so if you have a cantilever beam like this, you can run the most sophisticated FEA as you can. But, if you are trying to prove to me that, it's going to predict the stress, to the exact pinpoint location, to the exact decimal point, I think you're fooling yourself, right? So there's no model that can predict that with that much certainty. But with that said, there's some models that are out there that are useful for performing some engineering tasks. Okay, and I think that's always kind of a good saying that I keep in my brain, just to kind of ground me and make sure that I'm always being realistic with the tools that I'm using. Okay, all right. And so let's go ahead and answer this question now. So how do we assess how good or how reliable one model is compared to another one? Okay. And the 2 methods that are used to do this are verification and validation. Okay. And so oftentimes people call this V and V. Okay. All right, so let's define these first, and let's see what they mean. Okay, so first we have verification. All right, so verification, what this means is that we're assessing the numerical accuracy of our simulation relative to the true solution of the underlying equations. Okay. Okay. And so, of course, we're right now we're kind of limiting ourselves to mathematical models. Okay. And so whenever you have a mathematical model, when you have some kind of governing equation, and you go to try to solve that equation, okay, verification basically asks the question, am I solving the equations correctly? Okay. All right. And so, just for me personally, I hardly ever remember the exact definition for verification that I have there, but I always remember that question, right? And so, when I think of verification, I always think, I have these governing equations, I have these differential equations. Am I solving them correctly with the method that I'm using? Okay. On the other side, we have validation. Okay. And so validation, what this is it's an assessment of the accuracy of the mathematical model relative to the observations in nature. Okay. Okay. And so another way to think of validation is to ask yourself the question, am I solving the right equations? Okay. Another question you can ask yourself for validation is, did we set up the problem correctly? Right. And so one common issue with validation is your boundary conditions, right? And so a lot of times people ask themselves, are these the appropriate boundary conditions that represent the situation correctly? Okay, or do I need to change my boundary conditions to be more accurate? Okay. All right. And so to kind of help you visualize this, I have kind of a three-tiered kind of way to kind of think about this. Okay. And so on the one hand, the goal of any finite elements is you want to have some physical situation that you want to simulate. Okay. Okay. So that's the real life situation. That's the real life scenario that that you're interested in analyzing. Okay. The first step, whenever you want to perform analysis on this, is to model this with some kind of governing equation. Okay. Okay. So that step right there, it's a step we've kind of looked over a lot in this class. But if you think about when you open up ANSYS, you have to select an analysis system that you're going to work with, right? And so most of the time we pick static structural. And so when we pick static structural, we're assuming that the situation is static and it follows the equations of linear elasticity. Okay, but there's other options too. And so there's dynamics that we've seen. What you'll see later that there's modal analysis. Okay. And so you have to basically choose an equation or develop an equation that models your system. Okay. And so once you pick the equations, then you have to actually solve them. Okay. And so that's kind of this third step right here. Okay. All right. So that's kind of my three-tiered approach to engineering analysis, kind of in general, right? And so you have a physical situation, you pick equations to model it, and then you actually solve the equations. Okay. And so where V and V fits in is in kind of the two arrows here. Okay. And so validation, what you're asking yourself is, did I do this step correctly? Okay, so that's validation. Okay, because there's a lot of different ways that you can do that step incorrectly. Okay. And then verification checks this step. Okay. And so, in order to have like a finite element simulation that you can really trust and rely on, verification validation is extremely important. Okay, because if the finite element simulations were not reliable, then really it's no better than than having a monkey just feed you numbers from a program, right? And so for all we know, that might be what ANSYS is, right? And so we do all this sophisticated setup in ANSYS, but maybe it gets sent to ANSYS servers and a monkey just sends back numbers, right? And so that's possible, right? And so they could be scamming the world. But the reason we don't think that's true is because ANSYS as a company has done a lot of verification and validation. Okay. All right. And so in truth, V and V is actually a very, very, very long process. And so there's a very strict setup on how you set up like a validation experiment. There's a very strict way in which you can verify your code. Okay. And so it's usually not something that the average user will be expected to do. Okay. And so we're not going to go into all of that theory, because you can write honestly you can write a full PhD thesis on validating and verifying a code. But what I did want to focus on is what are things that you can do as a user to increase the faith, increase the reliability, increase the confidence in your simulation results. Okay, because at the end of the day, that's kind of what you have to do as a finite element engineer. Is you have to run the simulation, but you also have to be able to convince people that what you're getting from your simulations is actually reliable, is actually correct. Okay, and so some knowledge of how verification and validation occurs is I think really key to making that happen. Okay. All right. Any questions on this so far? Okay. All right. So let me start off by saying that verification, validation, very long process, but ANSYS has already done a lot of this for you. Okay. Okay. And so ANSYS has a whole company behind them that that regularly test their code, they verify their code, they run all these benchmark cases, they're validating against real data. And so ANSYS is doing a lot of this for you. And that's a big reason why you have to pay a lot of money for it. Okay. Okay. And so, if I know a lot of you have asked me throughout the class, but ANSYS is a very expensive software, partly because it's a fairly niche audience, and so not that many people are going to be buying it, but also it takes a lot of work to have a finite element code which is as versatile as ANSYS, and have it be as reliable and trusted as it is. Okay. And so part of what you're paying for is you're paying for that reliability. You're paying for that, you're paying for that, to trust that your simulation results are correct. Okay. But, with that said, even if you are using a very trustworthy software like ANSYS, there is still possibilities that you might not get results that are consistent with reality. Okay. Or to put it more bluntly, you can still mess up a simulation with ANSYS. Okay. And the ways that people usually mess up their simulations is they have either poor mesh quality or poor modeling decisions. Okay. Okay. And so, in order to prove that, your mesh quality is good, and in order to prove that your modeling decisions were sound, you can use some of the processes and verification and validation to show this. Okay. All right. And so, we've already talked about this a bit in the class, but, if you're going to go out in the real world and use finite elements, some degree of this reliability testing is required. Okay. And so, and really, there's no kind of exception for that. And so, if you're doing stress analysis for a company, you have to perform some of these tests to make sure that your stress computations are reliable. Okay. And this goes for research too. And so, if you're doing any kind of research work with FEA, you have to do some V&V just to make sure that your results are good. Okay. I can't tell you, how many research presentations I've been to, and people just dismiss results just because like a mesh convergence test wasn't performed or something like that. Okay. All right. So let's talk about what are some things that you can do in order to show that your mesh quality is good and your modeling decisions are good. Okay, so let's start with verification. And so, one big way that you can make ANSYS solve your equations incorrectly is to have your mesh be not very good. Okay, and so as we kind of already know, one way that you can show that your mesh is good is to perform a mesh convergence test. Okay. All right, so we've already talked about mesh convergence tests in this class, and so I'm not going to spend too much time on this. But remember, the idea with mesh convergence tests is that you rerun your simulation several times with different mesh densities. Okay. Okay. And then for each simulation that you do, you observe or you record a quantity of interest. Okay. Bless you. All right. And so when you have when you don't have convergence in your solutions, what we say is that you have numerical errors in your solutions. Okay. Okay. And when we have a numerical error, all we say is that, we have these equations, we're trying to solve them, but the mesh density just isn't there for us to get a good quality solution on them. Okay. All right. And so you've all seen mesh convergence tests, but let me just draw one, here just for completeness. Okay. Okay. And so if we plot the number of elements versus the quantity of interest, okay, eventually you should get it to a point, where the solution doesn't change value all that much. Okay. Right. And so you want to be somewhere right here where the solution starts to plateau. Okay. All right. And so, if you add this to any finite element study that you do, you kind of eliminate this this factor of mesh dependence. Okay. And so with that said, I know because I'm requiring it for the final project, and for those of you that did this for the midterm project, probably seen already that sometimes it's really hard to get mesh convergence. Okay. And a big reason why that you guys are probably going to struggle to get mesh convergence is the limitations of the software. Okay. And so the unfortunate thing with the student version or the academic version of ANSYS, they put a hard limit on how many elements you can have in a simulation. And I think, when you're first coming to finite elements, it seems like a lot. And so it seems like, the limit, I think for the academic version is maybe close to 100,000. Like I saw some reports that you had element counts in the 90,000s. And so that might seem like a lot, but in reality, it's kind of not. And so, for a lot of, practical finite elements that I've seen people do, I have element counts in the like 500, 600,000s. And for my own research, I usually don't feel comfortable unless the element counts are in like millions. And so, 2 million, 3 million, 4 million is pretty standard. And so, that's the kind of mesh density that, probably people are working with in industry. And that's why they kind of force you to buy the software, right? And so if you could perform real engineering work with the free version of ANSYS, then, ANSYS, the company is probably doing something wrong. And so, so don't, and so the point is, don't be discouraged if you don't get mesh convergence on your final projects. I would be very surprised if you could, actually, honestly. Okay. But it's still important to do. And so, even in industry, if you can't get mesh convergence, maybe your boss asks you to do a simulation in too short of a time. This is one way that you can show him that, definitively, here's the data that, I don't feel comfortable with the simulation results because we haven't reached convergence yet. Okay. And so this is one test that you can do to kind of show. All right. Any questions on this? Okay. All right. And so, in terms of verification with ANSYS, I'd say this is the most of what you have to do. Everything else that has to do with the verification has to do with, how the code itself is implemented. Okay. And so, of course, as a user of ANSYS, you don't have to worry about that. And so you trust that ANSYS is implemented correctly and, that it's devoid of any kind of major bugs. Okay. But I do want to say that, if you're going to be working with a software that's not ANSYS, okay. Okay. And it's becoming more and more common nowadays because of the whole open source movement. Okay. And so there's a lot of, honestly, really great codes out there that are open source and completely free. Okay. But, you have to realize that if you're going to use an open source code, they don't have the kind of team or the kind of resources that ANSYS does. Okay. And so all of the verification tests that ANSYS is doing, a lot of these open source codes probably are not going to be able to run the same thing. Okay. And that's mostly an issue of resources. Okay. Because if you want to do kind of a full kind of verification suite on a code, it takes a lot of resources in order to do that. It takes a lot of manpower, takes a lot of computation power as well. Okay. And so a lot of open source projects, a lot of times either just, one dude or two dudes, coding in their garage, and they want to share their code with the world, which is great. But you have to realize that there's a lot of limitations to this as well. Okay. And so if you are going to use a code like this, then I would highly recommend that you run some benchmark tests. Okay. And so just to see if the solutions that you get from this code make sense. Okay. Right. And so some example, and actually we'll talk about that later in terms of validation. But make sure you just, if you're going to be using a free code, just kind of make sure you do your due diligence. Okay. And if you end up developing your own code, this goes doubly, triply true. Okay. You want to make sure you do your tests, before you put a code out there for people to use. Okay. All right. And so that's verification. Okay. So now let's talk about validation. All right. And so validation, remember, validation asks the question of, are we even solving the right equations to begin with? Okay. And so validation is more concerned about the fact of, once we get these simulation results, is this actually what we expect to happen in reality? Okay. Or is this physically consistent? Okay. And so there's lots of different ways that you can perform validation. Okay. And, those different ways range in how effective they are. And so the way I'm gonna structure this is I'm gonna go from kind of the gold standard. And so this is kind of the best way that you can validate a code. It's also the most expensive, and then we'll go down from there in terms of what else you can actually do. Okay. All right, and so the gold standard for validation is to perform some physical experiments and take some experimental measurements. Okay. All right. And so, for some people, they consider this to be the only true way to validate, right? Because if ultimately the goal of your code is to simulate a real life phenomenon, then you should actually perform a real life phenomenon test and then compare the results of your code to that experiment. Okay. Okay. And if you're going to run an experiment with the explicit intent to validate against a particular code, then we call that a validation experiment. Okay. Okay. All right. And so the idea is that, if you to basically form a physical situation and then simulate that exact same thing in finite elements and then compare your results. Okay. All right. And so let me do an example with my favorite situation ever. And so we have a cantilever beam. Okay. And so let's say on the left here, we have the real situation. Okay. And so, in the real situation, we're actually going to build a real beam. Okay. We're going to apply a load. Okay. And then what we're going to do is, after we set this up, we're going to take some measurements. Okay. And so let's say that we measure. Okay. So let's say that we measure the deformation here. Okay. And let's say that on this part of the beam, we're going to put a force meter. Okay. And so we're going to measure the stress here. Okay. Right. And so that's the real life experiment. Okay, so that's something you have to perform in the lab with the proper equipment to perform the measurements. Okay. On the flip side, we're going to take this exact same situation and model it with FEA. Okay, and so with FEA, let's say that we put a mesh on this guy. Let's say that we have a bunch of elements. Virtually, we're going to be applying the load. Okay. And then we're gonna basically compute the same things. And so once we get our simulation results, we're going to measure the deformation there. Okay. And we're going to measure the stress in the exact same place. Okay. Okay. And so ideally, if your code is well validated, or if it's well constructed, then you should get the exact same things on both sides. Okay. Okay. And so you should get the same deformation at the tip, and you should get the same value of stress on the top of the beam like that. Okay. And so if you get the same results, then that's great. Then we say that your code is validated. Then we then it represents the physical situation now. But if not, then you're probably going to have to debug your code. Okay. All right. So very, very rarely, if a validation experiment doesn't go right, it's very, very rarely the fault of real life, because Mother Nature is not going to lie to you, and so Mother Nature is going to always, do what she's going to do. And so, if there's any kind of discrepancies, probably it's going to be FEA. But and I say that because sometimes when people try to do validation, they blame the experimentalists and they blame reality. But don't blame reality. Blame your crappy code. Okay. So I've seen a lot of this. All right. Right. And so this is, as you can imagine, this is really important because if your FEA simulation is not getting the same thing as reality, then it's not really going to be that useful, right? And so a lot of the things that we use FEA for engineering design, engineering analysis, it's kind of built on the fact that what we're simulating in FEA is a good representation of reality, right? And so until the validation is actually performed, then then it's not for some people they think it's useless, right? And I kind of agree, right? And so if your FEA simulation is getting something totally different from reality, then how can you actually say that you're going to use that to design a bridge or design a building, right? If you're not even estimating the deformations correctly, then that's not a good thing. All right. Any questions on this? Okay. Oops. All right. And so, what happens if you don't get matching results between your, between reality and FEA? Okay. And so, what are some possible things that could go wrong? And so I'll say probably the number one cause of discrepancies is in the boundary conditions. Okay. And so I would say this is, besides meshing stuff, I'd say this is probably the #1 cause of errors within finite elements. Okay, is people who don't use appropriate boundary conditions for the situation. Okay, and a lot of times this can be difficult to spot because if you use the wrong boundary conditions, and so if you use the wrong constraints or use the wrong loads, most of the time ANSYS is not going to give you an error, and so most time ANSYS is not going to tell you that this is not good, right? Because really that knowledge is up to you as the engineer, right? And so ANSYS has no idea what physical situation you're trying to model. ANSYS is just doing what you tell it to do, right? And so it's really up to you, the engineer, to say, this is the physical situation that I have, and this is how I'm going to basically encode it in terms of boundary conditions. Okay. And so proper boundary condition selection is really important because that really relies on kind of the expertise and the knowledge of the engineer itself. Okay. Okay. Right, and so it's always in my experience it always pays to like double, triple check your boundary conditions, just to make sure that they're reliable. Okay. Okay. And so that's kind of the gold standard for validation. And so if you have the resources to perform an experiment and to try to compare your results with finite elements, that's the gold standard. And so if you can do that, then you say your code is reliable and it's good to go. Okay. And the nice thing is that ANSYS has done a lot of these tests for you too, as well. Okay, and so they've taken a lot of canonical situations and they've run the physical tests and then they've compared the results with ANSYS and they saw that it was reliable. Okay, and so that's why and that's kind of partially what you're paying for as well. Okay, but with that said, even though ANSYS is running they've done a really good job validating their code against a lot of different situations. You have to realize that probably the situation that you're simulating is not quite the same as what ANSYS has tested. Okay? So every situation is unique. Okay. And and just practically speaking, it's impossible to run validation tests for every unique situation. Okay. And so even though a validation experiment is the gold standard, a lot of times it's just not feasible. Okay. And if you run a validation experiment, it kind of defeats the purpose of finite elements anyway. Because if you're running finite elements, what you're saying is that you don't want to run a physical test to begin with. Okay? And so the way validation is usually done is that validation experiments are done usually on a collection of tests, and then as a user, if you run tests that are similar to that, then we say that the results are validated. Okay. But with that said, there's other ways that you can validate your results that don't involve running a specific experiment. Okay. One way that you can perform validation without doing an explicit experiment is to compare your results to data that's been published elsewhere. Okay. All right. And so, in the scientific literature, there's people have done tons and tons of experiments over time. Okay. And so if you can simulate, the exact same situation as someone else has already reported to, and you can recreate their data, then that's another good way that you can perform validation. Okay. And I'll say that this method here of looking into the literature and finding an experiment to recreate, this is a very, very popular method among researchers. Okay? And so for people that are developing codes that maybe don't have the same kind of resources as ANSYS, but they do want to show that their code is reliable, a lot of times they're going to look into the literature and say that, let me try to recreate this experiment, this famous experiment, or let me try to recreate this data that these researchers found with finite elements, and then that's going to be my validation. Okay. And so this is, just kind of speaking from my own experience, this is very common in the medical field. And so if you, the thing with medical doctors is that, they're always taking a lot of measurements on stuff, and then they report their measurements. Okay. And so there's a ton of data out there in terms of, how well certain medical devices perform, or what the blood flow is like inside a person's, brain, right? And so for researchers that want to model those things with simulations, they take those papers and they try to recreate those results in simulation. Okay, and if they can do that, then that's great evidence that their code is reliable. Okay. All right, but even in cases where you don't have hard data, you can still perform validation against some physically observed phenomena. Okay. Okay. And so one kind of thought experiment that I had with this is, if you're familiar with the Space Shuttle Columbia, that was kind of a very famous space shuttle that broke apart upon re-entry. Okay, and so what happened with the Space Shuttle Columbia is that as the spaceship was taking off, a piece of foam actually fell off the space shuttle and struck the wing. Okay, and so it might seem like, oh, it's just a piece of foam, but with the speeds that the aircraft was running at, that foam actually caused some pretty significant damage to the wing. But the thing is, the astronauts and all the engineers, they couldn't fully observe the damage that it caused. But what they did know was that it did cause some damage. And so one way that you can validate your code is to take a situation like that and run it within finite elements and see if you can match up your simulation results with some of the things that they did observe. Okay, and so that's kind of another way that you can perform validation. Okay. All right. Any questions on this? Okay. All right. And so if you have real life data, either from a published paper or from some other observation, that's a great way to perform validation. But sometimes you don't have either, right? And so what do you do when you don't have none of the above? Okay. All right, and so if you don't have any data to validate against, but you still want to show that your results are reliable, there's still some things that you can do. Okay. And so one thing that you can do is you can check your simulation result against an analytical solution. Okay. And so what I mean by that is check against the result that you can compute by hand and see if you can recreate the same result. Okay. And so I'm going to go back to my favorite analogy. And so let's say that we have a cantilever beam. Okay. And so a cantilever beam like this, you can solve this by hand, because it's effectively a 1D situation. And if you assume that the, and if you assume that the beam deformation is small, then you can solve this using Euler-Bernoulli beam theory. Okay. And so Euler-Bernoulli beam theory, of course, is governed by a certain differential equation. Okay. And so if you solve that differential equation by hand and you get a solution for the deformation, and you compare that result to your simulation, and they're the same, that's one way that you can validate your result, because Euler-Bernoulli beam theory is pretty well respected. People generally believe that it's true. Okay. And so if you show that if your code or your simulations can match that reliable model, then that's one thing that you can do. Okay. But of course, that only really works if your geometry and your situation was simple enough that you can simulate it with the beam. Okay. Most situations that you're interested in doing FEA on are a lot more complex than this. Okay. And so let's just think of your project so far, right? And so if you look at the shaft housing or you look at the globe valve, right? So there's no way that you could solve either of those systems by hand. Okay. But in these situations, what you can do is you can do what I like to call a simplified model. Okay. Okay. And so what I mean by simplified model is to take your complex geometry and then kind of map it or kind of simplify as much as you can until you get it to the point where you can run a hand calculation. Okay. Okay. And so maybe for the globe valve, maybe you approximate it as just a sphere, right? So maybe you approximate it as a thin spherical shell, and then you apply an internal pressure, and then you can compute like the stresses, or you compute the deformations from that. Okay. And of course, it's not going to be exact, right? And so a sphere, is not a great representation for the globe valve, but it'll at least be close. Okay. And so if you can create the simplified model and you can run your hand calculations on that and compare it to your finite elements, then that's another way that you can verify. Okay. And so I've seen this a lot in scientific reports too, where people take their, they take their complex geometry and they simplify it. And they said, we ran these calculations by hand and we saw that the results that we're getting from finite elements are somewhat similar. Then that's a good sanity check to just to make sure that your results are in the right ballpark. Okay. Okay. All right. And so, the whole idea with this, and this might seem kind of silly, right? And so, if we're going through the trouble of doing a finite elements, why are we doing this, hand calculations, when it's going to be more crappy anyway, right? And so the whole idea with any kind of validation is to basically diversify your sources of information. Okay. And so I think because a lot of people kind of get into the trap where they run a finite element simulation and they think that that's like gospel. I think that that's the truth, right? But as with anything nowadays, right? Like you should always check so that you're not just relying on a single source of information, right? And so if you do an experimental test, or if you check against validated data, or if you even just do a simple hand calculation, if you can show that across different models or different sources that you're getting the same thing, that boosts your confidence up in your results, all that much more. Okay. And really, that's going to be the game that a lot of people play for computational work, because the main difficulty that people have in doing computations is not the simulation itself. It's just convincing other people that what you're doing is actually legit. Okay. Because a lot of people can really dismiss finite elements as like, oh, they're just playing on the computer, or they're just making nice figures and nice animations. But finite elements is legit, and I think a lot of times that onus is on the engineer to show that what you're getting from a simulation is actually reliable. And what we cover today in terms of verification and validation is some good ways that you can use to to actually show that this is true. Okay. All right. Any final questions on this before we wrap it up for the week? Question? Okay. Okay. And so I'm going to end this a little bit early. And so tomorrow's a holiday, and so we'll end a little bit early for that. Okay. And so next week we have another ANSYS week. And so on Monday we have a lecture that kind of introduces the concepts, and then Wednesday we're going to have the activities. Okay. All right. So thank you everyone for tuning in. Hope everyone has a good weekend. Hope everyone enjoys their day off tomorrow. And I'll see you next week.